This is Lab 4 for Physics 2211 on oscillations. The purpose of this lab was to use the video given and record the energy changes that the model computes. In addition, we were supposed to plot the energy changes from the model. Then we were supposed to compare the predicted motion and the observed motion of the mass in the x and y directions. The formulas used to do this were Newton's second law, change in energy, and the force equations for gravity in the spring. The initial position of the object taken from the video was negative 0.109, negative 0.654, and 0 meters. The initial velocity of the object was 0 meters per second. The mass of the object was 0.5 grams, and the change in time was 1.524 seconds. The total time was found by taking the final time, 6.762 seconds, and subtracting the initial time, 2.19 seconds, from it. To set up the computer model, I first defined all of the different forces. I set the gravitational force equal to 0, negative 9.8 times the mass of the ball, 0 newtons, and then I set the spring force equal to negative spring constant K times S, which is the actual length of the spring minus the relaxed length of the spring, times L hat, which is the direction of the spring force. Next, I set the net force equal to the sum of the gravitational force and the spring force. Then, in order to update the velocity and the position of the ball, I used Newton's second law and the momentum principle. In order to update the spring, I defined L as the position of the ball minus the position of the spring. L hat was set equal to L divided by the magnitude of L, and S was defined as the magnitude of L subtracted by the relaxed length of the spring. In my glow script model, I set K equal to 1/2 times the mass of the ball times the velocity of the ball squared. The potential gravitational energy was set to the mass of the ball times the gravitational constant times the y position of the ball. The potential spring energy was set to 1/2 times the spring constant times the compression squared. Finally, E was set to the sum of these three energies. Finally, the kinetic potential and total energy are all the same calculations from the previous slide, and the change in energies are equal to the current minus the initial. This energy graph shows the change in energy remains constant at 0, as shown by the orange line. This makes sense because the system is closed and no energy is leaving or entering. The graph also shows an inverse relationship between the potential energies. As the gravitational potential energy increases, the spring potential energy decreases. These graphs show the experimental position data in red compared to the model position data in blue. The graphs are pretty similar in the beginning, but as time goes on, there are more discrepancies. This is because the model does not account for drag forces that slow the ball down. Discrepancies could also be caused by human error when tracing the position in tracker. The energy principle is satisfied because the change in energy remains constant at 0. This is because the system is closed, so no energy is entering or leaving. The oscillation period when using X was found to be about 1.62 seconds, and when using Y, it was about 1.52 seconds. These differences would cause different K constants, a different spring force, and therefore a different net force. It is important to use the Y oscillation period since the spring force acts in the Y direction. And then